Welcome back to lesson 7. This is part 2, where we're looking at applications of differential equations. In particular, we're going to look at Newton's law of heating and cooling, boundary growth models, and the logistic curve. Start with boundary growth number 1, Newton's law of cooling. Newton's law of cooling states that the rate of change of the temperature of an object is proportional to the difference between its own temperature and the ambient temperature. Newton's law can be expressed as the following relationship. That is dt, which is temperature versus time, is proportional to T, subtract Tm, where T denotes the temperature after time T, and Tm is the temperature of the surrounding medium. The differential equation, therefore, with our constant K, is dt equals K outside of T take Tm. Example 26. An object is heated to 180 degrees Celsius and is then placed in a room that is maintained at a constant temperature of 30 degrees Celsius. After 4 minutes, the temperature of the object has dropped to 160 degrees Celsius. Assuming Newton's law of cooling applies, determine the temperature of the object after 10 minutes. Step 1. State a differential equation to model the object's temperature. That's a differential equation, which is a boundary growth type equation. Here, we know that our ambient temperature is 30, so that's Tm. Step 2 is to solve the differential equation. We invert both sides, so now we have dt over dt, temperature, equals 1 over K outside of T take 30. Now if we integrate both sides with respect to capital T, we end up with T equals 1 over K outside of the natural log of T take 30. Plus C, our constant of integration. To rearrange that further, we can multiply both sides by K. And to calculate the constant integration, we're then going to sub in our initial conditions, which was that at 0, our temperature was then 180 degrees. So therefore, 0 equals the natural log of 150 plus C. If we subtract the natural log of 150 from both sides, that's our C value. So now to determine K, we can sub that back in terms of here's our constant of integration. We now have Kt equals the natural log of this, take the natural log of this. Using log laws, we have the quotient of T take 30 and 150. We can now sub in our time, which is 4. At that point, the temperature was then dropping to 160 degrees Celsius. So 4K equals the natural log of 13 over 15. Now that can be evaluated using a calculator, and we can divide our answer by 4. Hence, to a few decimal places here, 5 decimal places, we have a K value. Hence, we actually now have our model. We can rewrite this now knowing that K is negative 0.03578. So to isolate this, we want to make an equation where T is the capital T is the subject. So therefore, we have e to this power equals T take 30 over 150. We can multiply both sides by 150, then add 30. Now we have a model for temperature. It's in the form of an exponential equation that is decreasing due to the K value. Step 6, determine the temperature of the object after 10 minutes. Let's evaluate the temperature at 10. Approximately equals 134.89 degrees Celsius. Boundary growth 2, which is in biology. Example 27. The mass of medium-sized cats is found to follow a boundary growth model. The initial mass of a typical newborn kitten is 150 grams, and after 20 weeks, its mass has increased to 1.5 kilograms. Given the maximum weight of the cat is 5 kg, determine the mass of the cat after 2 years. State the differential equation to model the mass. It's very similar to our last question because we have a cat that won't get above a maximum weight of 5 kg. So what we're going to do is work out this K value, and we can then develop a model similar to the Newton's law of cooling and heating. Solve the differential equation by inverting both sides, integrating both sides with respect to m, hence our left-hand side is t. We have another natural log here, but now we have 1 over k. If you're wondering why this negative 1's come here, the derivative of negative m is negative 1, so we're dividing that function here by negative 1. we now have the natural log of -1 lots of ln 5 take m plus c being the constant of integration. Rearrange by multiplying both sides by k. Calculate the constant by subbing in some values, which can be, at time 0, the object weighed 150 grams, which in kilos is 0.15. So C, after rearranging, is the natural log of 4.85. We can now sub that back into here and then hence make a model. Determine the equation that models the cat's mass. So as I said, we have our C value. Now here we've got -1 lots of a log. Now that -1 can be brought up here to become a power. So that'd be 5 take m to the power of -1, which would be 1 over 5 take m. So now if you're wondering what happens next, when I add these, I've got to multiply these two together, which is why I end up with 4.85 over 5 take m. Due to that -1, and then I would write it as 1 over 5 take m times 4.85 equals this quotient here. So now I have rearranged this. I'll have e to the power of kt equals this. To determine k, I'll sub in some values given in the question, which is at 20, the mass is now 1.5 kilos. So e to the 20k equals 97 over 70, or 4.85 over 3.5. And that's just simplified in terms of being exact value in terms of a fraction. So the natural log of that fraction, then divide both sides by 20. K approximately equals 0.06929. So we can sub that now back into our K, and we can write a model for our mass. So here, I'm multiplying both sides by 5 take m. I'm then going to rewrite this as being, I'm going to divide by e to the power of 0.06, etc., t. I now have 5 take m equaling 4.85 e to the -0.06929t due to using your index laws. And we could rewrite this. If we subtract this, as it is inverse operation, bring it to the other side, and bring the m to the other side, we'd have m equals 5, take 4.85 e to the -0.06929t. Determine the mass of the cat after 2 years. That's 104 weeks. We sub in 104. We have 4.996 kilograms. So it's nearly at its maximum weight. Next, we're going to look at logistic growth. In many cases of population growth, there is obviously a finite upper boundary m, the carrying capacity, which the population size p must approach. This is called inhibited or logistic growth. Consider a species with an initial population of 5. Graphically, this looks like something like this, which is at time 0, the population is 5. Due to the limited resources, such as food, water, or shelter in the habitat, the population will never exceed 200. That is, the ceiling, m, is 200. Graphically, we've drawn that as an asymptote at 200, or y equals 200. Here's our starting population, and here's our ceiling. Initially, the population will grow exponentially, but will level off as it reaches the carrying capacity. This looks like the following. So with an initial population of 5, initially we start to rise at an exponential rate that starts to level off as we reach our carrying capacity. This is an example of logistic growth model. The logistic differential equation itself can be written as either dp dt equals kp outside of m take p, where m is our carrying capacity and p is our population, or another commonly used one, which is kp outside of 1 take p divided by the carrying capacity. A generalized solution to the second model, dp dt equals kp outside of 1 take p over m, is the following. So our population model is P equals m over 1 plus AE to the negative KT. P is population, M is carrying capacity, K is the growth constant, T in this case, most cases is time. Note that A is the carrying capacity, subtract the initial population over the initial population. Now we can solve that differential equation to show that this is a generalized solution. Two graphical examples are shown below of further logistic models. Example 28a. Solve the differential equation to show that PT equals m over 1 plus ae to the negative kt. Rearrange the differential equation and begin integration. That is, we're going to rearrange it by separating the variables. So we've divided both sides by 1 take p over m, and then we've multiplied both sides by dt. So the right side's pretty easy. The left-hand side, we're going to have to use a combination of techniques to integrate. Step 2 is to integrate the right-hand side with respect to t. Hence, that is kt plus c. Rewrite the left-hand side. So begin by multiplying by m over m. We now have m over mp outside of 1 take p over m. I'm then going to multiply, expand m through this expression here, which is why I end up with m, subtract p, because the m's are going to cancel out. Now that we have this, before we integrate, we want to apply partial fractions. So this quotient, using partial fractions, this is not showing the full working, but if we show full working, we'd end up with 1 over p plus 1 over m take p. Now we can anti-differentiate that left-hand side. So the integral of our partial fractions is the natural log of p take the natural log of m take p. Next, we're going to apply log laws. So using log laws, that becomes the natural log of p over m take p. Now we're going to be able to equate the left-hand side and the right-hand side. So this is our result of our left-hand side. This was our right-hand side. And this next step, I've now written it as m take p over p instead of p over m take p. I've raised it to the power of -1. Using our log laws, I can now write that as -1 lots of that natural log of this. I'm then going to multiply both sides by -1, which is now I have negative kt take c. I can use my log laws, that's log base e, so therefore it's e to this power equals m take p over p. I can now use my index laws here and separate the e to the negative kt and the e to the negative c by writing multiply sign between the two as their like bases. Next, we know that a is actually e to the negative c, so now I have a e to the negative kt. Our last step is to make p the subject. In that case, I'm going to divide m by p and p by p, which is why I now have m over p take 1. I can add 1 to both sides. Now rewrite this as p equals m over a e to the negative kt plus 1. And there is the solution, the logistic differential equation, as required. Where p is the population, m is the carrying capacity, a is the ceiling carrying capacity, take the initial population divided by the initial population, k is the growth constant, and t is time. Example 29. The maximum number of koalas that can be supported by the environment of a national park is approximated to be 3,000. When first counted, they were found to be 1,200 koalas, but after 4 months the number has grown to 1,300. Determine the parameters for the logistic model and use them to calculate the number of koalas after 1 year. Step 1. State the differential equation. So stating one of our differential equations for logistic growth is our first step, where the following parameters are p for population, m is the carrying capacity, and a is the carrying capacity subtract the initial population divided by the initial population, and t is time. Next, we're going to apply the generalized logistic model for population growth. That is, we're going to use the general population model without having to solve a differential equation. So step 3 is determine the parameters. Now, A was our 3,000, take our initial population, or divided by our initial population. So A is at 1.5. Hence, our ceiling is 3,000, A value is 1.5. Now the next step is to only find this K value. To do so, we know that at time 4, the population has now grown to 1,300. So subbing in our 1,300 and our 4, we're now going to rearrange and solve for k. So 3,000 over 1,300, we can now subtract 1 from both sides, divide both sides by 1.5. To isolate the negative 4k, we'll take the natural log of that quotient, then divide by negative 4. K approximately equals 0.0343. Hence, we have our population model, which is the state logistic model. Now answer our question. Step 5 is to determine the number of koalas after 1 year. And note that 1 year is 12 months because the model was in months. So substituting in 12 for t, approximately there are 1,504 koalas. Depending if you're rounding up or down, there's roughly 1,505 koalas over the 12-month period. That concludes lesson 7. To test your understanding, complete the following question. Environmental officers filled a lake with 400 crabs and estimated the carrying capacity, the maximal population for the crabs of that species in that lake, to be 10,000. The number of crabs tripled in the first year. Assuming that the size of the crab population satisfies the logistic equation, determine an expression for the size of the population after 2 years. Use this model to calculate how long it will take the population to increase to 5,000.